Okay, any questions about anything? So yeah, you can ask me questions in the middle of the class if they come to mind, or you can ask on Slack to so today we are going to basically talk about the last topic of the semester, which is equilibrium constants. I think we will be able to finish it today. We might have a little bit left that we will do on Friday. Definitely not more than 15 minutes worth or 20 minutes worth on Friday. After that, on Friday, Monday, and Wednesday, so almost 3 full classes, I will be doing a full revision of as much as I can of the semester. Instead of and for this, it will be very helpful if you all send me either direct messages or just post on the channel for this as to what are the topics you really want me to pay attention to. That way I can focus. Maybe you don't want me to talk about everything. I will try to give an overall gist, draw the big picture, because if you just focus on a couple of topics, you might not be able to form the big picture. So I will try to give a big picture of the subject, but then I am interested in focusing on specific topics. Chemical potential, for example, we did last week. That is so complicated that it confuses people. So we did that. So think about that and post your topics today. And since it goes on till Wednesday, do it over the weekend. Really go through the material and try to look at things that confuse you. And let me know what they are so I can help you before that. Okay. So let's talk about equilibrium constants. This is something you have probably seen in chemistry, in general chemistry or something else earlier. And it's easy to talk about equilibrium constants. That's why it's introduced at a very early stage, even high school stage, perhaps. It depends on where your high school is and how much chemistry you take there. But now we are going to look at it in the light of our superior knowledge of thermodynamics. What do we mean by equilibrium constant? So we know that dg at constant temperature and pressure less than zero is condition for spontaneity, right? This is the condition. So any process will happen in the direction in which the Gibbs free energy goes down if you're looking at constant temperature and pressure. If you're looking at constant temperature and volume, then you have to think about Helmholtz free energy. But at constant temperature and pressure, this is the thing that you care for. So what does this mean for a reaction? This means that if you have a reaction, let's say some generic reaction where A could convert to B and B could convert to A. In this case, the composition of the reaction, and we want to figure out that at equilibrium, how much of A will we have, how much of B will we have. So what we are going to use this statement as, we will re-express it as that composition of a reaction mixture changes at constant T and P. So if we had constant T and volume, then we had to think about Helmholtz free energy, constant T and P until G is minimized. So dg stays negative, it becomes as small as it can, and then it cannot go down any further. That is what we care for. Once g is minimized, EQBM, equilibrium, is, sorry about that. Once it is minimized, equilibrium is attained. So let's try to quantify this notion, this physical concept, in context of some reaction A interconverting to B. How do we do that? So let's look at a general setup where we have, and I'm going to use the notation from Atkins. I think Atkins uses this Greek symbol for this. This is the symbol xi. I don't know, or zeta, whatever you want to call it. I'm going to call it xi, Z-I, xi. I'm sure it's spelled something else. It's Greek. I don't know Greek. It's pronounced xi. It's probably PSI or something else. So I'm just gonna write it as a squiggly thing. You can just call it D squiggly thing. That's also okay. So let's consider that D psi, a small amount. By minimize, does that mean most negative or closest to zero? The change is negative. The G becomes as small as possible. The G goes and then it cannot go any further. Whatever value is constrained. So it becomes as low as possible. If it was to go any further, G would go up. So it goes and stops over here. And we will see that here. And we will quantify this exactly right now. So let's say D xi moles of A, some small number of moles of A, convert to D xi moles of B. How do we know that the number of moles of B and A will be 1:1? Because that is our reaction. A interconverts to B. If we had A in going to 2B, then it would be different. So once this happens, the change, and again, everything is at constant temperature and pressure. I'm not going to write it again and again because I will forget at some point. So just keep in mind, all of this discussion for equilibrium constant is at constant temperature and pressure. So xi represents the change in A. How much did A decrease by? How much did B increase by? And we are talking about some small amount of change. So you can think of xi is as a progress variable for the reaction. How much has the reaction progressed? And you're talking about small progress in the reaction by d xi. So then in this case, dg will be given by, how do we write down dg? We know at constant temperature and pressure, dg is mu I ni, right? So chemical potential is what it is at constant temperature and temperature, constant pressure and temperature, and what changes is n, the number of moles of the species. So dg will be given by mu A multiplied by minus d xi, because A has converted to B. So the amount of A has gone down, plus mu B multiplied by plus d xi equal to mu B minus mu A multiplied by d xi. This is our change in Gibbs free energy. So we can write down that partial G by partial xi, change in Gibbs free energy with respect to change in progress of the reaction. This is how much of the reaction has actually happened at constant pressure and temperature, is going to be mu B minus mu A. Okay, now super important thing here is that this is not mu B naught or mu A naught. This is mu B and mu A. There is a difference between this and mu B naught. For example, mu B for an ideal gas is something like mu B naught plus RT ln P B, right? So we have to figure out what is mu B, and that's how you can see the temperature and pressure start to play a role in this equation. Even though it is at constant pressure and temperature, these are functions of pressure and temperature. In other words, we can define a reaction Gibbs energy for the reaction that we wrote above, this A interconverting to B. The reaction Gibbs energy, which Atkins calls as delta Rg, just like we had mixing Gibbs energy, this is reaction Gibbs energy. Delta Rg is equal to mu B minus mu A, because this is the change in Gibbs energy that happens when the reaction proceeds per mole. You can think of it that way. So this shows us that if delta Rg is negative or mu B is lower than mu A, forward reaction A going to B is spontaneous. And if delta Rg is positive, that is mu A is smaller than mu B, then backward reaction B going to A is spontaneous. So in one of the classes when we were discussing chemical potential, one of you had asked me, how will you measure chemical potential? You can look at it also by looking at the chemical reaction, which way it is happening. The key thing to keep in mind is that the chemical reaction will tell you about mu B. It won't tell you about mu B naught. So you have to do a bit more math if you care about mu B naught. Typically, mu B naught is also reported at standard pressure and temperature. So this is yet another reason why chemical potential is useful. It can tell you the reaction is going to happen in which direction. Now let's take a closer look. So far we haven't really, I just mentioned that this is a function of temperature and pressure. Oh, by the way, regarding the videos for the midterm, I'm having a great time watching them. All of you have done a wonderful job so far. I haven't seen a video which is bad. All of them are great. Some are funny. There are going to be 2 funny prizes, which means you're entitled to ice cream with me at Maryland Dairy when it opens up. We will have to wait, and if you graduate before it opens up, we will find a way to do something else. But there are going to be 2 teams. One team I have already decided. Second team one team had some inside help, and I will explain that later. So that team is definitely going to get ice cream. They were great, but they had inside help. So there are going to be 2 prizes. So there is a question. Delta G reaction is automatically per mole. That's correct. It is the molar reaction free energy. So we have said here that this mu B minus mu A is a function of temperature and pressure. But what is this function? Let's try to quantify this. So let's understand delta RG bit better. Starting with ideal gas. And this is why we start with ideal gas, because it allows us to write down something mathematical. And then you have seen, this time you will actually see how it gets directly. We'll start with ideal gas, we'll derive our expressions, and we will show the final expression that works for anything. We just replace our mole fraction with activity, with the understanding that we have to measure the activity coefficient experimentally, but the math directly takes over. So starting with ideal gas, what can we say? We can say that mu is equal to mu naught plus RT ln P by P naught. This will be true for A, this will be true for B. So therefore, delta RG is equal to mu B minus mu A is equal to mu B naught plus RT ln PB by P naught. And P naught doesn't need to have an A or a B because it is just a reference pressure, minus mu A naught minus RT ln PA by P naught. Okay, so this becomes mu B naught minus mu A naught plus RT ln PB by PA. Okay, so this is our delta RG. Now you can see you have separated out, for an ideal gas, you have been able to write down explicit dependence on pressure and temperature. And that's interesting, that's powerful. You know exactly how does it depend on temperature and pressure. So now we define something which is labeled as Q, and it is called as the reaction quotient. We are not quite at the equilibrium constant yet. Equilibrium constant is a special value of this reaction quotient. So this reaction quotient is defined as PB by PA, this pressure over here. This is the ratio of partial pressures. For an ideal gas, it's defined this way. We will generalize it soon. So just to make sure that you have a sense for what we are talking about, I want someone to help me and tell me what happens to the reaction quotient if we have only A. If system is equal to only A and if system is equal to only B. What will be the value of Q in the first case? If you haven't received participation points, now is the chance to jump and get them. So unmute yourself and tell me.
If we have only A, would it go to 0?
Why?
Because the numerator would be 0 if there's only A.
If only A, then denominator will be 0, right? There is no partial pressure of A.
Oh. So would it go to infinity then?
Yeah, so the thing to keep in, no, you're correct. If it's only A, repeat what you said. If it's only A, what will be the value of PB?
0.
Why is that true?
Because we think of pressure as the collisions of the gas particles against the container.
Yeah, there is no B. And more importantly, the partial pressure is mole fraction of B multiplied by the total pressure, right? And the mole fraction of B is now 0. So you're absolutely correct. Q is 0. Yeah, thanks, Tyler. So if you have only A, then Q is 0. And similarly, if you have only B, then Q is infinity because now B is 0. Thanks, Tyler. So Q captures how much, Q captures where you are in this reaction. You know, it quantifies how far, is it only A or is it only B? It's just a mathematical way of looking at it. So we can write this down now as, let's label our equations. Let's call this equation number 1. Then equation number 1 can be written down as delta RG is equal to delta RG naught plus RT ln Q, where delta RG naught is mu B naught minus mu A naught, right? So this is equation number 2. Now at equilibrium, what do we know? We just wrote down that at equilibrium is when the G, the reaction Gibbs equilibrium, is when that the Gibbs free energy cannot increase in either direction. It is, there are more questions. Equilibrium is when delta RG is equal to 0. The change in Gibbs free, if delta RG was positive, it means that you haven't reached equilibrium. You are going to keep changing in one direction until it goes down to 0. If it was negative, you would keep going in the other direction until it goes up to 0. So delta RG is equal to 0 at equilibrium. No, what does this, if this confuses you, delta RG is just a bigger version of DG, right? DG is differential, delta RG is looking at a bigger change. So we know that DG less than 0 is spontaneous in one direction, DG more than 0 is spontaneous in the other direction. Therefore, DG is equal to 0 is equilibrium. In other words, delta RG is equal to 0 is equilibrium. What does this mean for us? This, if you use equation 2 over here, this means delta RG naught plus RT ln Q is equal to 0 at equilibrium, right? At equilibrium, the value of Q is called K. At equilibrium, and this stuff gets confusing. The reason that we had Q and we never really use it, but like I said, it's only at equilibrium that Q becomes K. In other words, minus RT ln K is equal to delta RG naught, right? If we take this equation, we take this to the right-hand side and we are talking about equilibrium. So we can replace Q by K. So minus RT ln K is equal to delta RG naught, or RT ln K is equal to minus delta RG naught. That's our equilibrium constant. How do we write down this equilibrium constant in terms of partial pressure? Is delta N, no, it's delta, what do you mean delta N, Matt?
The change in Gibbs free energy per mole, the very last, or in the very last equation where you have the equilibrium constant equal to.
Oh, this one, delta R, it's R, by the way.
Oh.
Delta R G naught. Good question. That depends on A and B, right? If A and B have mu A naught equal to mu B naught, if you landed in that unfortunate condition, then no. Then delta RG naught will be 0. Otherwise, it can be positive, it can be negative. So if it is, so that's a good point. So if it is positive, if delta RG naught is positive, that means ln k is a negative number, or k is a very small number, right? So that's exactly what tells you which direction will you go in. Yeah, it could be 0 by accident if mu a naught and mu b naught are exactly same. I would be surprised if it happens. It would happen when a and b are exactly the same, right? Otherwise they should be different. Otherwise, there is nothing to happen. So in other words, what we have done here, just to recap, is that we defined Q as the ratio of PB by PA, right? Any pressure, it might not be, yeah, so just I'm answering exactly your question, Anthony, right now. Q is equal to PB by PA, K is equal to PB by PA value at equilibrium. Okay, so Q is defined for any pressure. You can stop the reaction from happening for whatever reason, and you could still measure your Q. Or the reaction is maybe still going on. You are coming and checking in your test tube and the reaction is still going on. Once the reaction stops happening and you measure the partial pressure of B and the partial pressure of A, their ratio is K. So K is just a very specific type of Q. And we can write this down for a general reaction. So we looked at A going to B. Let's write down a very, very general reaction. A most general way of writing a reaction is to write it down as 0 equal to some species J multiplied by with their stoichiometric coefficients nu multiplied by J. This is a general reaction. What do I mean by this? For example, if you have 2A plus 3B going to C plus D, this is, or I will stick to what I have in my notes so I don't make a mistake while I'm trying to explain. If I have 2A plus B going to 3C plus D, then this reaction can be written as 0 equal to minus 2A plus minus 2A minus B plus 3C plus D. Or in this notation, you have nu A equal to minus 2, nu B equal to minus 1, nu C equal to 3, nu D equal to 1. Yeah, so this is the general reaction. You have some species J or component. The species versus component thing is confusing. I know Elizabeth has been confused about it. So this is a slanted nu, slanted V, yeah, it's a nu, it's a slanted V with subscript J. This is the stoichiometric coefficient for the species J. So A is the first value of J, which has the stoichiometric coefficient minus 2. B is the second value of J, which has the stoichiometric coefficient minus 1. You bring everything to one side, so you have plus sign for the products in your original reaction and negative sign for the reactants. It's just concise way of writing the reaction. So now we can write down our Gibbs free energy for this generic mixture of species. Again, we have n moles of the species J. So in this case, our J is going from A to B to C to D. You could have a general reaction where instead of A, B, C, D, you have A plus B plus C plus D plus E going to F plus G plus H. The summation will just run over more indices. We won't be in exam and stuff. I won't be giving you some abstract general reaction. I will give you a specific reaction to look at. But if you understand this, you can deal with any reaction. So in this case, we can write down the G as mu J Nj summed, where J goes over all the species in the reaction that are participating in the reaction. And you have to be careful with species or components. So therefore dG is going to be J mu J dNj, right? We are not changing the chemical potential because it's happening at constant pressure and temperature. All we are changing is the number of moles of species. And then we can use our progress variable and write it as mu J nu J d psi. Where did this come from? If I go back and look at this at your notes after the class is over if it confuses you, but this is a direct restatement of what we wrote over here. For A, we had mu A minus d psi. Why did we have minus d psi? Because the coefficient of A here was -1 if you write it in the general format, while the coefficient of B was +1. So you have minus d psi with mu A and plus d psi with mu B. Here you will have mu J d psi in a general setup, and you don't have to worry about minuses and pluses because they are accounted for in the mu J, in the stoichiometric coefficient. So now we can write down our Gibbs reaction Gibbs energy as partial G by partial psi at constant pressure and temperature. So this is all at constant P and T. This will be simple now because we just go in and differentiate with respect to this. All that happens is that the progress variable disappears. We are left with mu J, nu J. Or we can keep the nu J and put in the mu J as mu J naught plus RT ln. And now we are going to bring the big guns. The equation that I'm going to write next is super generic. And how do I need to go? How do I go from ideal to real? Instead of mole fraction or partial pressure, I just bring in the activity, AJ. And this equation that I wrote down over here is absolutely any reaction that you can think of. Any chemical reaction. This is no ideal, there is no regular, no behavior, no van der Waals, nothing, because you have brought in activity. And last time we taught about activity, that activity is related to an activity coefficient multiplied by the mole fraction. And it's really kind of cheating because you need to do experiments to measure your activity coefficient or do some simulations, but not really. The form is so simple. What we wrote down earlier for a two species ideal gas is now completely generalized to any chemical reaction with as many species as you want and happening with in real, no ideal behavior. Furthermore, let's call this as equation 3. This is super important. Like I said, this is so general. We can write it as summation J, nu J, mu J naught plus RT. RT comes out. Let me clean that up. Summation J, nu J, ln AJ. Let's go to next page and start from this one. So what do we have so far? We have delta RG is equal to summation over all species of nu J mu J naught plus J RT nu J ln AJ. So we are going to call this as delta RG naught, right? This is the reference value. Can you re-explain how did you substitute nu J, Zj for D and J? Yes, I can. Think of the best way to understand this is the reaction A going to B. In that case, D and A was equal to -1 multiplied by D psi. D and B was equal to +1 multiplied by D psi. And that's what we have done over here. If instead of this, you had 2A going to B, then what would it have been? D and A would have been -2 D psi. D and B would have been plus D psi. And that captures really chemical intuition. 2 moles of A need to be killed before 1 mole of B is born, right? That's the idea over here. And that's why the stoichiometric coefficients show up. I'm going to have a problem on the final exam on this because the final exam is like a mega homework where you don't talk about things to each other. So you will think through this. So it's what you're doing is trying to understand this part is important, and then the final exam problem will be easy. It will be easy. So now we have, let me rephrase it. I might have a final exam problem on it. No promises of any sort. I'm going to be like a politician. I might keep my promises. So this is delta R G naught, just like we did for our A-B reaction. We had mu B minus mu A, and we wrote it as delta R G naught. Now instead of mu B minus mu A, we have summation mu J naught, where again, if you get confused, go and look at the AB reaction to make sense of how this happened. And you will see directly how it happened. So this is defined as delta R G naught. And here we can do something. We can keep the RT and RT and keep the summation over J and take this new J and bring it to the power, right? That's the nice thing about logarithmic functions, that nu can go inside and it can be raised, the activity can be raised to that power. So what is this? I mean, there is a reason that the logarithm shows up so much in thermodynamics and statistical mechanics. It's almost as if it shows up to deliberately make our life easy, but there are deeper reasons for that. So now we can write down this summation explicitly. Let's write it down to get some intuition. Let's say the J goes from 1 to 2 to 3. These are the chemical reactions. So if we had a reaction where 1 plus 2 plus 3 are acting to compare to 4 plus 5 plus 6, these are our species instead of A, B, C. So then this can be written as ln A1 to the power nu1 plus ln A2 to the power nu2 plus ln A3 to the power nu3 plus ... It will actually be ln A4 to the power nu4 plus ln A5 to the power nu5 plus ln A6 to the power nu6 for this reaction that I wrote over here. And notice I didn't put any minus sign because that is already accounted for in nu. Okay, but in general, you will have ... as many as it goes. Now that we have this thing, we can do yet another trick with the ln and realize that ln of x plus ln of y, like this log plus this log, is equal to product of logs, right? Sum of logs is equal to log of products. That's the most amazing thing about logarithms. So this is RT ln A1 nu1 multiplied by A2 nu2 multiplied by A3 nu3 ... So the summation is now gone and we have a product inside the log. And in math, there is a symbol for the product. It is written as a big pi. So this is a bigger pi. And it is going over all species j. And it goes aj to the power nu j. This is our delta Rg, now written in a different form. So equation 3 and equation 4 have exactly the same information. I have just done a little bit of manipulation. So we can generalize our reaction quotient now. We generalize. And just give me 5 minutes. We will come back from the land of math to the land of actually thinking about chemistry just in 5 minutes. But I want to do this in a full framework because it's so powerful. We can generalize the reaction quotient Q as Q is equal to not the RT, but the thing inside the ln. Aj to the power nu j. And again, to give you intuition, if you had A happening going to B, then this would be product over AA to the power nu A multiplied by AB to the power nu B. And in this case, nu A is -1, right? Because you take the reactants always have the negative sign and the product has the sign +1. So this is equal to AB by AA, right? And that is what we wrote down earlier. Q is equal to, we wrote down Q is equal to PB by PA, but that is for ideal gas. For real gas, it is AB by AA for real gas. Activity will always be given. Yeah, you will be given the activity coefficient. Like I said, there is no way you can derive the activity coefficient from theory. So you need to do either computer simulations to get it, or you need to do experiments. So the connection between activity, if it's a real material, all I will do is to tell you how does the activity vary with mole fraction. So in other words, I will tell you the activity coefficient. If you know the activity coefficient, you are ready to go. I mean, in principle, I could have given you yet another homework on this, but this semester is long enough. And if I did that, then you would have very little time to do your exam. So that's why I decided we do it this way. Okay. And with this, we can once again write down delta Rg is equal to delta Rg naught plus RT ln Q. This is something we wrote down for our model, little A going to B reaction, and now it's generalized to everything. Let's look at another reaction. For example, let's say we have 2A plus 3B, and I want one of you to help me with this, C plus 2D. And I want you to tell me what is nu A, nu B, what is nu A over here in our framework? Just chat, write in chat, it's sufficient. 2?
-2.
-2, correct. And how about B?
-3.
And nu C is 1, and nu D is +2, +1 and +2. So let's write down our Q. Q for this one is going to be AA to the power nu A, which is -2, AB to the power nu B, which is -3, AC to the power nu C, which is 1, AD to the power nu D, which is 2. So this is AC AD square divided by AA square AB cube. So we wrote down our Q for this one, correct. And so let's go to next page. So we wrote down so far that delta Rg is equal to delta Rg naught plus RT ln Q. Once again, at equilibrium, we expect delta Rg is equal to 0. Therefore, delta Rg naught is equal to, and at equilibrium, we called Q is equal to K. The value of Q at equilibrium becomes K, the equilibrium constant. Therefore, once again, delta Rg naught is equal to minus RT ln K. We saw it for A times A going to B, but it's the same general thing. And now, K, the equilibrium constant, is product over all species J of their activities Aj raised to the power stoichiometric coefficient measured at equilibrium. So you need to measure their activities at equilibrium. So K, so the take home here is K is Q at equilibrium and tells us a constraint on different species. What do I mean by constraint on different species? Let's look at, and thermodynamics is really a constraint. We say minimize your free energy, maximize your entropy. These are all constraints. The system, from a very mathematical perspective, thermodynamics is in a surface, in a three-dimensional space, which is made up of N, V, and E. The entropy can take any value, but all that thermodynamics tells us is you have to be constrained to a surface, which is unique and given as a unique function of N, V, and E. So that's why these constraints show up again and again and again. I got a bit abstract here. If this doesn't make sense, that's okay. I will talk a little bit about this in the revision perhaps. But for now, let's be practical and just think about our equilibrium constant. So what do I mean by constraint? And what is this K really telling us? To look at this, let's look at a reaction where A in gaseous form can exist in equilibrium with B with its stoichiometric coefficient 2, also in gaseous form, okay? So what will be the value of K for this one? What will be the power of activity of B? Any idea? Same as last time, +2, absolutely correct. And A? -1, right? So the A goes in bottom. So this is at equilibrium. Let's assume perfect gas for now. Even before that, I want you to answer, like I said, we are going to stop with the math now. I want you to answer something very physical. Let's say this A and B are existing in a container where they can stay under equilibrium, and I increase the pressure on this container. If I increase the pressure on this container, what do you think will happen to the reaction? Will it become... Yeah, Elizabeth is still worried about species and components. Depends on whether a reaction is happening, whether is the H2O decomposing into something else. If not, then you just treat H2O as a species. If H2O is splitting into H and O, then you have to consider H and O. So you have to look at the smallest individual reaction that's going on. And that's the thing that you consider here for your A and B. Okay. So my question for you right now is, if you increase the pressure on this reaction, will it mean... So let's take a step back. Let's forget about increasing the pressure. Let's just consider equilibrium. At equilibrium, if we assume a perfect gas, what can we say about AB? We can say that AB is equal to PB by P naught, right? Because it's a perfect gas, so it's just the partial pressure. And AA is equal to PA by P naught. Therefore, K is equal to PB square by P naught square multiplied by P naught by PA is equal to PB square by PA multiplied by P naught. Notice one thing that happened. Your K is dimensionless, right? And this is super important. K should always be, when you write down an expression for K and you are getting a dimension, if you're getting that it's pressure squared divided by only pressure, something is wrong. K should be dimensionless, because if it is not dimensionless, you cannot take its log. You cannot take log of a quantity with a dimension. So K should be dimensionless. So this is something you can always check. So we know that a given reaction is going to have a fixed value of the equilibrium constant. Why? Because the equilibrium constant is related to delta RG naught. We know the reaction, we know the species that are taking part in the reaction, A and B. We know their stoichiometric coefficients, in this case -1 and +2. So we can look up the table for their mu A naught or their mu B naught, some chemistry table, and calculate their delta RG naught, right? That is just going to be, for this reaction, 2 mu B naught minus mu A, or something like that. So we can calculate their delta RG naught as a constant. So the equilibrium constant is, it's called constant for a reason, right? It's equilibrium constant. So at equilibrium, we know that PB square by PA P naught is equal to K, is equal to constant. It has some value. And this tells us a constraint on the ratios. Would you not divide AB by AA? Why? If I'm talking about the reaction A going to 2B. If I'm going A going to 2B, then I divide AB square by AA, not AB by AA. Is that clear, Stephen?
So for your K, you say that PB squared over P naught squared times P naught by PA. Oh, okay, I see it. Never mind.
See it? Yeah, it's confusing. Good. No problem asking. You know, in general, when you all go to a chemistry seminar or anything, always try to understand something, but if it's not clear, ask. No professor is going to judge you for having asked something. And then when you understand it, just like Stephen did, say, oh, I get it. And that's totally okay. So this is a constraint. Now my question for you is, if I increase the pressure on this container, what will happen to the reaction? Will the amount of A increase? Will the reaction suddenly start to be favoring this direction, or maybe this direction, or will it stay as it is? Is the increase in pressure on the system going to change the direction of equilibrium? Any idea?
I think it will favor the reverse reaction, because the partial pressure of B will increase more than the partial pressure of A.
So, okay, I got you, Brianna. So yeah, you have to help me now. So now if I increase the net pressure, what will be the, let's say the reaction stays as it is. Then what will happen to PB and what will happen to PA? First, will they increase or decrease?
Both will increase.
Perfect. And they will increase for an ideal gas. Will one of them increase less or more?
Since PB is 2 moles, or
No,
for
but
since
don't think about the reaction. If the reaction stayed as it is, if you stayed at the equilibrium value of A and B, if the mole fraction is not changed, then how will they change? Then they will change equally, right? Okay, I see what's confusing you. So what I mean to say is that PB is equal to XP multiplied by P, correct? And PA is equal to XA multiplied by P.
mhm.
So they will both change proportional to P. That's my point.
Yeah.
Correct? However, in the equilibrium constant tells us that the effect of, thanks, you can unmute yourself if you wish. The effect of B on the equilibrium constant is square. It's twice and in a power as relative to the effect of A. So if you let both B and A increase, the partial pressures of both B and A increase, this number, this Q over here, this Q will increase, it will shoot up. The Q will really shoot up, right? It's a subtle argument, but you can see what's going on because PA increased by a certain amount, PB increased by a certain amount, but here over here you have a square. So Q just shot up. So the system has to compensate for that. And the way to compensate for that is only if this XA starts to increase. And this is the point that I'm going to discuss again. So in next class, I'm going to start with this, exactly this point. I will start from this reaction and again try to understand it in terms of pressure and in terms of, we will also look at the effect of temperature before we start our revision. So the point I'm making here is that Q is equal to PB square by PA P naught, while K is equal to PB square by PA P naught at equilibrium. If net P increases, then PB increases, PA increases, but effect of PB on Q is much more than that of PA, right? Because PB comes up with a square. Is this Le Chatelier? Yeah, this is Le Chatelier. I don't know how to pronounce it. My French is crap. The only French I know is by listening to Daft Punk, who don't really sing in French. So the way this can be compensated is that PA must go up. How should PA must go up? So you increase the total pressure and that causes PB to go up and PA to go up. PB goes up at double the rate because it's power 2. PA has to catch up. How can PA catch up? PA can catch up in two ways: by the total pressure that you cannot affect because that is for the full system. The other way PA can catch up is by compensating the XA. Therefore, XA must go up. Therefore, the reaction becomes favored in this direction when the pressure is increased. And this is exactly our Le Chatelier principle, pardon my French. Now, you can go through the reverse argument and think about if net P is decreased, then PB drops down, PA drops down, but PB squared drops down much faster than PA, and that's what you have in the ratio over here. Therefore, to keep up for this, XB, and so you are looking at the ratio of PB squared by PA and the P naught, and this term is dropping down very, very quickly, while this term is dropping down slowly. So you want this term to drop down faster. This has to drop down faster to keep up with the numerator. And why do we want to keep up with the numerator? Because if we don't do that, then Q, which was equal to K at equilibrium, will become non-equal. Therefore, XA must go down. Therefore, A going to 2B becomes the preferred direction. And this is exactly Le Chatelier principle. Next time, we will look at the effect on temperature. If you want, we can. So we will look at how, we will write this down in terms of something called the degree. We will look at this once again, just in a slightly different perspective, not too different. and we will talk about effect of temperature, and that will be last thing. Next class, 20 minutes into the class, I will start revising from the very, very beginning. Please ask me questions on Slack or through direct message or on channel, so I have an idea what you want me to focus on. I will also be having office hours next Monday. Please try to come to that and discuss things with me. So you have 3 classes and 1 office hour to, not next Friday. The next Friday, I will be releasing your exam. So today is 2nd, right? 9th December is last class. 11th December AM, exam is out. And then you have a week to finish the exam. Okay, so I can teach you more, but no. And then if I did a next class next Friday, then you get less time for the exam. So what's the point? Go work on the exam. So I expect lots of discussions on Slack, and please help your classmates. If something is really obvious to you that is correct, please go and answer them on the channel so I can see. So don't mislead. If you do it in direct message, there is a small chance you are misleading your classmates, which is fine if that's what you want to do. But post on channels and someone can correct, no, I don't think this is right. Let's have a discussion. Okay, good. So see you all on Friday. No class on Monday 14th. No, that's exam time. So the last class is 9th of December. 11th to 18th, you have to focus on the exam. It's going to be longer than the midterm. It's going to be a fun, it will be a type 2 fun exam. No, just kidding. It will be 1.5. It won't be more than type 2. It will be type 1.5. Okay, so see you next class on Friday, this Friday.